Good morning and welcome to Group 4's presentation on Lab 1, Flow Measurements through a Rotameter, Orifice Plate, Soap Bubble Meter, and Wet Gas Meter. Group 4 is comprised of Asya, Miriam, Shamira, and Rayolin. Introduction. Flow measurement is an important requirement for processes as it ensures that there is a certain rate and that there is no obstructions in the pipe, therefore maintaining a desired product quality while guaranteeing the efficiency and effectiveness of the system. Flow rate is dependent on the following variables: fluid velocity, liquid density, viscosity, and friction between the fluid and the pipe. Fluid flow is measured using different flow meters. In this experiment, we'll be considering the soap bubble meter, rotameter, orifice plate, and wet gas meter. The accuracy of these measurements are ensured by calibrating the equipment and installing the setups properly. The intentions of this experiment is to determine the appropriate and most accurate flow meter by measuring the flow rates of liquids and gases using the previously mentioned flow meters, as well as to determine how the sizing of the flow meters affect the flow rates.
In the following 3 slides, a brief on each flow meter used in this experiment will be given. In a rotameter, the flow rate is measured by varying the cross-sectional area through which the gas or fluid flows. The force that is created by the fluid flow results in the float moving up to a particular height, and this height is then used to calculate the flow rate. And the following is the equation used. In an orifice plate, the flow rate is calculated by measuring the pressure drop that occurs as a result of reducing the area of the pipe. The soap bubble meter is used to calculate airflow measurements, and the following is the equation used, where L is the distance the bubble travels, A the cross-sectional area of the cylinder, and T the time taken for the bubble to rise between the two markings. The wet gas meter measures the flow rate by using the principle of positive displacement, and the following is the equation used, where V represents the volume. The results in a flow measurement laboratory test work conducted by M.B. Kime, where the experiment was aimed at evaluating the accuracy of different flow meters, found the following. Soap bubble meter and wet gas meter were found to be suitable for measuring low flow rates, whereas rotameters were found suitable for both low and high flow rates. Rotameters with greater diameter produced the more accurate and precise results. It was also observed that water flow measurements were more accurate than air flow measurements. Overall, the report had concluded that rotameters were the most suitable device for flow measurements, as they were able to accurately measure results for a wide range of flow rates.
Experimental procedure: the airflow measurement using a rotameter and soap bubble meter setup. A dilute soap solution was prepared and added to the soap reservoir. Valve 1 was opened for the entirety of the procedure, and the thermometer and manometer was used to maintain constant temperature and pressure of the system. Valve 2 was then varied to change the float height of the rotameter. It was evident that the float height is directly proportional to the flow rate. The time it took a bubble to reach a certain height in the bubble column was recorded. Water flow measurement using a 10S, 14S rotameters and a 1/8 inch orifice plate. For the 10S rotameter, valves 3 and 4 were closed, while valve 2 was varied, therefore changing the float height and consequently the flow rate. For the 14S rotameter, valves 2 and 4 were closed, and valve 3 was varied to the desired float height. The orifice plate, only valve 4 was adjusted to the desired pressure reading, which was determined from the readings of the manometer. The time taken to fill the cylinder to a certain volume was recorded for each setup. Airflow measurement using a rotameter, orifice plate, and a wet gas meter. Valve 1 was opened for the entirety of the procedure, and the pressure gauge was used to maintain air inlet pressures. Valve 2 was varied to desired float heights of the rotameter. The mercury manometer was used to measure the pressure in the pipe system, and the water manometer was used to measure the pressure drop across the orifice meter. The time it took the needle of the wet gas meter to make one complete revolution was recorded.
Results and discussion. The soap bubble meter experiment. Figure 1 illustrates the effect of rotameter height on volumetric flow rates of a gas using a soap bubble meter. The experimental flow rate was calculated by dividing the volume of the bubble by the time it took the bubble to travel through the desired height. Figure 1 shows that the volumetric flow rate is directly proportional to the rotameter height. The manufacturer's curve and the corrected manufacturer's curve also coincide, and the experimental flow rate is similar to the theoretical data. As the flow rate increases, the soap bubble meter has a greater percentage error. Therefore, soap bubble meters are better suited to measure low flow rates to ensure accuracy and precision. Rotameter and orifice plate experiment. Figure 2 illustrates the effect of rotameter height on volumetric flow rate through a 10S rotameter. The 10S rotameter performed well, as there is a strong correlation between the manufacturer's curve and the experimental curve. The manufacturer's curve and the corrected manufacturer's curve coincide. This shows that the 10S rotameter is more accurate in measuring liquid flow rates. Figure 3 shows the calibration chart of the 14S rotameter when measuring volumetric flow rates of water. The manufacturer's curve and the experimental curve correlate well, as the discrepancy between the curves remains small for the different rotameter heights. However, as the flow rate is increased, the standard deviation increases, which decreases the overall precision. From the 14S and 10S rotameter results, it can be seen that they are best suited for measuring liquid flow rates rather than gas flow rates. From figure 4, it can be seen that the experimental curve and the actual flow rate curve differs to a large degree, and this indicates poor accuracy. The orifice plate is subjected to a large degree of error as there is head loss associated with it. For the two rotameter and orifice plate setup, it can be seen that the 10S rotameter is more accurate than the 14S rotameter, as the 10S rotameter curve shows more of a resemblance to the manufacturer's curve. Wet gas meter, rotameter, and orifice plate experiment. Figure 5 illustrates the effect of rotameter height on volumetric flow rate of a gas through a 14X rotameter. The manufacturer's curve and the corrected manufacturer's curve coincide, as the correction factor was close to unity. The experimental curve and the manufacturer's curve differ up to a height of 30 cm. Thereafter, the difference between the two curves lessens. Therefore, the 14X rotameter would be best suited to measure the volumetric flow rates at high rotameter heights. Figure 6 illustrates the performance of the orifice plate. The experimental flow rate curve is seen to differ largely from the theoretical flow rate curve at all pressures, which indicates a high level of inaccuracy. The large difference between the curves can be as a result of a calibration error or faulty instrument being used. The wet gas meter is better at measuring air flow rates at lower volumetric flow rates. Rotameters and orifice plates are suitable for both water and air, with rotameters having a higher degree of accuracy compared to the orifice plates.
Conclusion. For the soap bubble flow rate setup, the soap bubble meter is more reliable at lower flow rates. As expected, the soap bubble meter becomes less accurate as the volumetric flow rate increases. This is the limitation of a soap bubble meter and should only be used at low volumetric flow rates. For the two rotameters and orifice plate meter setup, the experimental curve for both the 10S and 14S show a resemblance to the manufacturer's curve. However, the 10S rotameter curve shows more of a closer resemblance, indicating it is more accurate than the 14S rotameter. For the wet gas meter setup, there is a large discrepancy between the experimental and manufacturer's curve as the volumetric flow rate increases, as seen in figures 8 and 9. This could be due to human error or equipment error when the readings were taken. The wet gas meter and soap bubble meter are better at measuring air flow rates at lower volumetric flow rates, with the soap bubble meter being more accurate of the two. The orifice plate meter and the rotameters are suitable for both water and air. However, the rotameters have a higher degree of accuracy compared to the orifice plates. Recommendations. It is recommended that proper calibration of the flow meters is required before proceeding with the experiment to ensure proper comparisons between the different devices. It is also advised that the person taking the readings from the devices remains constant for all the different flow meters. This includes the person that is operating the stopwatch.